Sí.
¡Hala! Seguro que este era súper bueno.
Uno, uno, dos, tres, cuatro. Estamos haciendo una comprobación en el salón de actos. ¿Una algo? Ocho, nueve, 10, 12, comprobación. Toma, no.
Eh. Gustavo, pase por caja. Hemos encontrado su maleta. Un poquito de delay. Tiene un poquito de delay. A ver, le queda también, le da rollito, ¿no? Como un poquito de... Sí.
¿Aló? Rubén, ¿sí oye? ¿Se ha encontrado tu viejato que se encuentra en la parte de atrás? Por eso.
No, sí, funciona. Sí, vale. Y ahora te la paso. Sí. Sí, yo digo la pregunta, y eso sí que se puede llevar el tiro. Ah, sí, hay un montón de cosas. Tengo que cerrar. Hay un montón de cosas en mi universidad también, un montón de cosas de colección interna de la universidad. Tiene un sentido así. Muchas cosas absurdas que no digo. No para nada. Ok. Ah, vale, sí. Pues sí, no, pero no. ¿Sí? ¿Llega? Vale. Hello everyone, welcome back. Welcome to day 2 of the Granada Seminar. We have some amazing talks for you lined up, and I'm going to start with Pedro Mediano from Imperial College. Will be talking to us about higher order interactions and computation in brains and machines. So whenever you like, Pedro.
Wonderful, thanks so much. Can everyone hear me at the back? So good? Wonderful, excellent. Well, like John Lennon said, it's wonderful to be here. It's certainly a thrill. Thank you so much for the organizers. It's really great to be kicking off the second day of this Granada Seminar. It's been amazing so far. So, as Samuel just said, I'm going to talk about higher interactions and computation in brains and machines. Now, a little bit about myself. I am an associate professor of computer science at Imperial and of psychology at UCL in London. But at heart, I'm actually a physicist. However, I don't tell that to my boss. So what I'm going to do is I'm going to be talking about this kind of intersection between neuroscience, complex systems, complexity science, and computation, and kind of all. Hopefully, I'll convince you by the end of the talk that there's actually some really interesting connections between the three of them. I'm budgeted. Well, I plan to talk for about 40 minutes, so there's still time for questions at the end. But if there's any question throughout the talk, just feel free to raise your hand, and I'll be happy to chat. Before I actually start, let me give a quick shout out to the people that actually did most of this work. So at Imperial, I lead the Machine Intelligence and Neural Dynamics, or Mind Lab, with all of these really brilliant students. And I also want to give a special shout out to some friends that have been really instrumental in doing this work, mostly Fernando and Andrea down there from Sussex and Cambridge. You'll see Fernando wandering around throughout these days, so you can also ask him if you have any questions. And this is how this talk is going to go. So I'm going to start with this kind of very comprehensive and detailed picture of the motivation behind all of this work, and I will, with probability 1 minus epsilon, run out of time towards the end. But let's see how all of this plays out. Good. Let's get moving. So let's talk about computation, right? Typically, when we think about computation in a computer science sense of the word, we think about systems like, Harvard architectures or Turing machines and all of those, right? Something that takes in a string of inputs and processes it in some particular way and spits out some output, like an automaton or something of the sort. Now, there's quite a variety of models of computation, but one thing that is in common across most of them is that they are typically centralized around a single control unit. That could be the head of the Turing machine or the CPU in a Harvard architecture, or the control unit or any of those, right? However, and this will come as no surprise to a complexity science audience, there are many systems where computation happens in a radically different, self-organized way. And two classes of systems that I'm particularly interested in are neural circuits in biological brains, as well as artificial neural networks, which at the end of the day, they're also self-organized assemblies of lots and lots of quote-unquote neurons that find their way to perform some computation collectively. And this idea of decentralized or distributed computation is not new. And one of the canonical examples of these are stellar automata that we're also very closely familiar with in the complexity science literature. So on the left, you can see the famous rule 110, which is Turing universal, Turing complete, meaning you can emulate any Turing machine you want with a 110 stellar automaton initialized in careful ways. So it can actually perform any computation that any Turing machine can. And on the right, that is another stellar automaton, first reported by Melanie Mitchell, I believe, that takes a majority vote of the inputs. Right, so that's again performing a very specific computation. And in both of these cases, I would describe broadly what these things are doing as collective computation, right? Which is some computation that is instantiated through complex systems composed of many interacting parts. And it's precisely those interactions that made that computation happen. And let me take this one step further. Many computations that we care about, that are of interest, depend irreducibly on 3 or more elements. Now, let me give a few examples. So, from neuroscience, we have things like apical and basal dendrites from a neuron and an output, right? So we have contextual and receptive field input and so on. Several, multiple inputs happening at once. We have tons and tons of neurons in artificial neural networks. If you remove a chunk of them away, of course, the neural network will lose computational capacity. So it's something about the interaction. And you could say the same thing about protein folding, social phenomena, like social interactions, ecosystems. I could spend a long time giving examples that you already know. So the point that I want to drive with all of this is that complex computation relies crucially on high-order interactions, by which I mean interactions between 3 or more components. And the common principle behind all of these high-order interactions and all of these systems that I've mentioned above is this concept of synergy that I'll be talking about quite a lot. And synergy has been described informally for a very long time in the complexity literature from Hacken and many others. And informally, by synergy, we typically refer to somewhere or some phenomenon where the whole is more than the sum of its parts. Very broadly understood, right? So there's an intuition that we're trying to capture, the whole being more than the sum of the parts. We will see throughout the story that we can actually put this intuition into math and operationalize it and do really interesting stuff with it. So with all of that set up, let me now go into and formulate some more specific questions that I'm going to try to answer throughout the talk. The overarching goal of my research program is to make a theoretically and empirically driven investigation of collective computation in biological and artificial brains, with the kind of underlying thread or the underlying idea that using a complex systems perspective can reveal new insight or new commonalities between brains and machines. So some specific questions we're going to try to ask are: can we quantify collective computation from observed data? I'm going to answer yes. In particular, I'm going to answer yes thanks to the concept of synergy. Then we will ask how much synergy is there in the human brain and where is it? And finally, can we induce synergy in learning machines? And what is it good for? Like, is there a causal functional role of high-order interactions for artificial computations? So the take-home message, if you get out of this talk remembering one slide, make it this one. So I claim that synergy can be quantified empirically with computationally efficient estimators. That synergy, in fact, from a statistical mechanics perspective, arises in systems dominated by frustrated interactions, and that it reveals links in emergent computation across brains and machines. These are my key messages. I hope I'll convince you throughout the rest of the talk. If you want to go back and answer some more emails now, that's fine. You can do that as long as you remember this slide. So I'm going to structure my talk in 3 parts. First, we're going to talk about quantifying high-order interactions through synergy. Then we're going to talk about synergy and human intelligence. And finally, about synergy and artificial intelligence. Any questions so far? Okay, I'm doing a great job. Good, so let's jump and talk about high-order interactions. And before we talk about high-order interactions, we had a really beautiful talk from Anna about this yesterday. I want to add a little twist on this notion of high-order interactions, and in particular, I think it's important to make one very clear distinction between 2 sort of possible meanings of high-order interactions. And that is a distinction between what we call mechanisms and behaviors. In this paper from commentary in Nature Physics a couple of years back. So what do I mean by natures and behaviors? By mechanisms and behaviors? However, the mechanisms are basically what the system is, right? The generative process that gives rise to the system. It could be something like a Hamiltonian, some structural coupling in ODEs or something of the sort. Whereas a high order behavior represents, roughly speaking, what the system does, right? So statistical patterns of activity, or otherwise any patterns of activity in the resulting behavior or trajectories of the system. As a simple example that we put forward in the paper, in the case of an Ising model or some sort of spin model, the mechanism would be, for example, the Hamiltonian that actually determines the generative process, the interactions in the generative process of the spin system. And then once you simulate, or once you kind of see how this Hamiltonian plays out, you have some observed behavior that corresponds to the probability distribution across system states. And somewhat surprisingly, it turns out you can have high order phenomena, so interactions beyond triplets or beyond pairwise in one, but not in the other, and the other way around. Right? So it makes sense to me, at least, to kind of disambiguate between these two different possible meanings of high order interactions. So throughout the talk, I'm going to stick to this terminology of mechanisms and behaviors. Now, when it comes to quantifying these things from data, one is clearly easier than the other, right? So when we are faced with a new data set, we typically don't have access to its mechanisms. And when I say a new data set, I mean, for example, neuroimaging data from some brain, right? We have some idea of how, neurophysics works, so we have some idea of what brain regions interact with which, but by and large, we don't have to, right? So we can only infer behaviors from the data. So this is the kind of system or the kind of schematic picture that I'm talking about. You have a brain, you have maybe a few electrodes inserted here and there, and you have joins time series of activity. Right? So what we want is to quantify behaviors, and specifically high order behaviors, from that observed data. So what I'm going to try to do is do a systematic study of high order behaviors, specifically through or with the tools of information theory. And there are many other ways to do this, but I'm going to pick information theory because I think it's particularly valuable and it's flexible. So now let's take a bit of a turn, and let's move and talk specifically about using information theory to measure high order behaviors. To do that, let's take a step back and let's revisit some of our stats. And one of the first things that come to mind when you start thinking about stats and high order interactions is that not all correlations are equal. And let me explain briefly what I mean by analogy. So let's say you have two random variables. That could be anything, right? It could be, again, in the cases that I think about, they're normally activities of two neural populations or something else, but any two random variables. These two can either be correlated or, as we say, coupled or not. Right? So they're either correlated or independent, coupled or independent. And this is measured perfectly by the mutual information. Because mutual information is zero if and only if two variables are independent, no problem. If you want to see as an analogy, I see this as two rings that are kind of interlaced with each other. Right? So if the two variables are independent, the two rings are free. If the two variables are related, then the two rings are locked. And that's all fine and good. Now what happens when you move to having three of all variables? Now things get really interesting, because now we can have qualitatively different kinds of correlations. And importantly, some of them are visible from the past and some of them aren't. So let's do a quick thought experiment here. Let's focus on the set of rings on the left. Some of you may have seen them before. These things are called the Borromean rings. Let's do a thought experiment. Look at the rings on the left and imagine that the green ring magically vanishes into thin air. So it just disappears. What happens to the other two rings? They come apart. Right? But when you don't, when the rings are in that position, they are completely interlocked. Right? So you cannot take them apart, but if one of them were to disappear, the other two come. Let's do the same exercise for the rings on the right. Now what happens if you grab this little ring on the bottom right and you make it disappear? The other two remain locked. Right? So this is, in a sort of geometrical, topological way, a very, very good analog for these two qualitatively different kinds of interactions. The interaction on the left we're going to call synergy. The interaction on the right we're going to call redundancy. So synergy is a kind of interaction that is only visible at the high level when all of the system components are observed. Redundancies are higher interactions that remain visible even when one of the systems, one of the components is observed. Is that distinction clear? Excellent. Good. Now let me give you a slightly more operationalized version, or a slightly more operationalized description of synergy and redundancy. Right? What we're going to do is now in slightly more information theoretic terms. I'm still going to, not do lots of maths, but let's try to give a slightly more operational flavor to this. And we're going to do this by solving a mystery, which is the mystery of who stole the cookies in the seminar. Right? We come out of the coffee break and the cookies are all completely gone. I hope they're not, but as a thought experiment. And to do that, we call Sherlock Holmes. We call our friends in London, bring Sherlock Holmes to do a bit of an investigation, and we come up with this list of 9 suspects. Right? And imagine that now we start with a uniform distribution, because we really have no clue who of these 9 individuals could have been the despicable soul that took all of this. And we call 2 witnesses forward. Right? So in the language of information theory, what we say is that these 2 witnesses are sources of information. They're going to tell us something that's going to reduce our uncertainty about who of these 9 people stole the cookies. Right? Now, the first speaker, or first witness, says that the suspect had a moustache, and that allows us to cross out some of the suspects. And this is providing information in the strictest sense of Shannon theory by virtue of excluding probability mass. Before we knew this thing, we had some probabilities across some particular domain, some support. After we know this, some of the probability mass is excluded. So we gain some information. Another thing the witness says is that the suspect was wearing, or the culprit was wearing a hat, and again we cross out some of those suspects. Same with the other speaker, or same with the other witness, sorry. The culprit had a moustache, and the culprit had brown hair. Again, or red hair, and again we cross it. Now we have a funny situation, right? Because if you look at the information provided by only the first witness, you are unable to pick out the culprit. If you look at the second witness, again, you're unable to pick out the culprit. But when you have access to both sources of information at the same time, then you can tell that it was that guy who stole all the cookies. So if we now do a bit of a, instinct big mashup between information theory and set theory and try to formulate this with notions of set, kind of intersection and union and such, we can broadly put forward the following picture, where the information that both witnesses provide together is this kind of big set over here, and the intersection, so the information that we get from both, we call the redundancy. Information that we get from one but not the other, we call it unique information. And the information we get from the combination of the two, or sort of the quote-unquote, somewhat equivalent to the union, we call synergy. And this was formalized in a really, really beautiful paper from Williams in 2010 called partial information decomposition, or PID, where the mutual information that both sources X1 and X2 have about a target Y is split into these 3 kinds of terms: redundancy, unique information, and synergy. And in particular, in case it wasn't clear so far, synergy is that kind of information that quantifies information contained in the whole, but not in the parts. And therefore, it is a prime candidate to quantify these aspects of collective computation, high-order interactions, and so on and so forth. As a quick interlude, I really like Venn diagrams, and part thanks to PID. So of course, that Venn diagram is very close to my heart, as is that one, multidisciplinary, zoology. As a European living in Britain, this is a Venn diagram I very much agree with. And also that one is a Venn diagram that I find particularly intriguing. So, moving on, let's look at a very specific example now. And let's look at the XOR gate, which is the perfect and minimal example of synergy, provably so. So let's look at the standard XOR gate, where we have 2 inputs, X1 and X2, that produce an output Y. And this is the standard truth table of the XOR gate, right? So essentially the output is 1, if and only if exactly one of the inputs are 1. Okay, so it's a sum modulo 2. Now what makes the XOR very special? What makes the XOR very special is that you know only one of the inputs, you know absolutely nothing about the output. Right? So the mutual information between one of the inputs and the output with either of the inputs is exactly the same. Nonetheless, if you know both of the inputs, now you can predict the output perfectly. Right? So the mutual information between both inputs together and the output is identically 1. So the XOR is the statistical analog to those Borromean rings we saw earlier, right? Where if you see all of the variables, you can see a clear, very strong statistical structure. As long as, or as soon as one of them is missing, any of them, then you're completely down to chance, right? And you're out of luck. You can't predict. Is PID and XOR relatively clear? Does the analogy between XOR and the rings make sample sense? See nods, so we'll take that as a compliment. Good. So how does one actually go and calculate PID values from data? I'm going to be extremely brief on this. If you want, I can elaborate, but just to kind of give a very, very brief glimpse into one actually does this. So the way that one calculates PID values from data is you first start by setting up a system of equations that comes from the definition of PID itself. So you say something like the mutual information that the first variable has about the target is equal to the redundancy, so whatever they have in common, plus the unique information from itself. The same equation from the second variable, so whatever they have in common, plus the part that's unique to the second source, and then the mutual information of both of them together are equal to, well, the sum of all 4 things. Right, that's what we're saying. Good. Now, if you're an attentive reader, you may immediately pick up an issue with the system of equations, which is that we have 3 equations but 4 unknowns. And that is widely considered an issue. So what do? We need to add something else. And that something else, it would be, it would seem a really straightforward thing to do. Nonetheless, 15 years later, this is the thing that people still argue the most with. So what extra ingredient do you need to add? There's a number of ways. A typical thing to do is to add a formula for redundancy. The formula that Williams and Beer proposed originally in 2010 was this particular formula, where for each source you find the minimum information it provides about y, and then you do some shenanigans. And I don't want to get into details, but it's some kind of analog of the intersection of the information that all of the xi's have in common about y. You calculate this thing, and then you plug it in here, you solve that system of equations, beautiful, you're done. And that's effectively how one calculates the system, how one computes PID values from data, once you have those probability distributions. And that's all fine and good. For 2 variables, that's no problem at all. The only issue with this is that it's mathematically elegant, but it's horrendously expensive. And so the number of equations in this system actually grows according to, I believe, the Dedekind numbers of the second kind, or something silly, which means that when you have 9 variables, so until very recently, we could only calculate this up to 4 variables. Last year we had a paper where we managed to go up to 6. When you go to 7, you can't even fit the equations in. I think it will take about 400 terabytes of data to store the equations. When you go to 9 variables, we can't compute the number of equations there are. So it scales really badly. Now, hopefully this convinces you that calculating stage redundancy in large systems is computationally challenging. And this might seem like a really bad news when you're trying to do complex systems, because, well, we care about large stuff. Luckily, that's not the case, right? Because although calculating specific values of synergy and redundancy is very difficult, calculating the balance between them is actually very easy. And one way to do that is with this thing called the O information that Fernando and I came up with a handful of years ago. So this metric of the O information that we kind of represented with the symbol omega is basically what n equals 3 is equal to the difference between the information provided by the whole and the information provided by the parts. Right? So this is also a very straightforward interpretation of the whole minus the sum of the parts. And the O-info has this very useful property that the sign tells you whether the system is redundant or synergistic. So, for example, if you grab a system that's very redundant, where all of the variables are copies of each other, then your mutual info is greater than 1, because that should be a Y. Your O information is positive, and that means that everything is redundant, so it's all doing the same thing. When x1, x2, and y are linked by an XOR, then the O info is negative, and that means that it's synergy dominated, right? So negative O info means synergy, positive O info means redundancy. So you have this very useful way of calculating the balance between the two. And I'm not really going to go through the details, but actually we showed in a paper last year, I think, that the O information is in fact provably the only measure that provides a balance between synergy and redundancy, and is computable in linear time. Right? And linear time is something that, has, if you're interested in large systems, then that's something. Good. Now let me take a bit of a turn, and I'm going to get a little bit into the statistical mechanics of synergy. And this is some really beautiful piece of work from PhD student Enrico Capriogio from Sussex, who started investigating the network origins of synergy. And one question that's been going on in the field, if you've been kind of paying attention to this kind of literature, is the question of whether high-order behaviors can emerge from low-order mechanisms. Right? So the kind of things that people normally do, or one common thing to do, as we saw in Anna's talk yesterday, was you start with a system that has a high-order interaction built in, so you have like a high-order Hamiltonian or a high-order Laplacian, and then you see how the system behaves. Now I'm asking sort of the opposite question. Can I have a system where the interactions are pairwise? And is it possible that the resulting behavior is high order? And the answer is yes. And to a surprise, this came out linked very directly with frustration. So I don't want to show too many equations, but this one is very beautiful, not efficient. It turns out that to a leading order in the spectral radius of the covariance of a system, the O information is equal to the trace of the matrix to the cube. And so here W is the correlation matrix of X without self-loops. So effectively you have the correlation matrix of a system, you set all of the ones to all of the diagonals to 0, and you do all possible loops, or like all possible walks of length 3. And if those are negative, you have synergy. If those are positive, you have redundancy. And that allows us to do a thorough, like a complete enumeration of what we call synergistic motifs. Right? So the minimal sub-networks that lead to synergistic interactions versus minimal networks that lead to redundant interactions. So when you have frustrated systems, for example, two variables positively correlated and one variable negatively correlated, when you take the product of this cycle, you get a minus, so that contributes to synergy. The product of this cycle also contributes to synergy. The product of this cycle is positive, so you get redundancy, and the same for this one. So there's this very, very close relationship between synergy and frustration. We also link this to these older theories of structural balance and so on. There's lots of really beautiful theory to read out here from the statistical mechanics. Good. A quick proof of concept on a little simulated model, which is Stellar Automaton. I've been making all of this fuss about collective computation and high-order business, but does it actually correlate at all with any meaningful notion of computation? So let's go back to Stellar Automata, those like classical examples. One thing we know in Stellar Automata is that Wolfram defined or classified the Stellar Automata in 4 complexity classes, 1, 2, 3, and 4, that you may have often seen. So what we can do is grab all of the elementary Stellar Automata from each of these classes and calculate this balance between synergy and redundancy. And lo and behold, synergy is higher for more complex automata. Right? In particular, these class 4 Stellar Automata are theorized to be Turing complete, are the ones with highest synergy, or with the highest difference between synergy and redundancy. And this, I'm forgetting the citation again, but this was a paper in Chaos, I think 2022-ish, a few years back. Okay. So these are the correlation level. It does seem that synergy is tracking computation in complex systems, or distributed computation. Good. Let me take a breather, do a bit summary. So what we've seen so far is we've made this distinction between high-order mechanisms and high-order behaviors. We've introduced some practical algorithms to quantify synergy, and we have seen that low-order mechanisms can generate high-order behaviors via frustrated coupling. Are there any questions so far? Okay, let's move on. I'm doing only partially well with time, so I may have to speed up. Let's look at synergy in brains, right? So now we have introduced all of these theoretical mathematical apparatus to interrogate collective computation, to look at synergy, to look at higher order information stuff. Let's now apply this, right? So first of all, we're gonna ask, what does this have to do with computation as it happens in the human brain? So here's a very quick overview of the analysis. In terms of data, we grabbed neuroimaging, fMRI, like resting state fMRI data from 100 subjects from the Human Connectome project. We did the usual pipeline of pre-processing and denoising and parcellating. So for those of you that are not very familiar with neuroimaging data, you end up with effectively about 200-ish multivariate time series. So for every subject, you get a joint, like a vector multivariate time series of about 200 variables or so. Then we grab pairs of brain regions, and for each pair, we compute their synergy and redundancy, and that gives us two networks, right? So one network of synergistic interactions and one network of redundant interactions. And the first thing we can do is, well, aggregate those, take the balance between them, and see how the group average. And what we see is this. So here is a map of what we call the synergistic core of the human brain, colored such that red regions are predominantly synergistic and blue regions are predominantly redundant. And now, this may not look like much to you, but if you stare at that brain long enough, you will recognize some very, very clear patterns in this map I'm showing here. So for example, this part over here is this is looking at a brain kind of from the right, as you would be looking at my brain from where you're at. This part over here is a frontal cortex, so a prefrontal cortex. And that's usually the part that has to do a lot with high-level cognition, like inhibitory control and lots of what we consider high-order cognitive functions, or high-level cognitive functions. Whereas this band over here is the somatomotor cortex that effectively sends signals back to your muscles, right? So we start to see a yes. Not for this one in particular. Like this data, you can also do that, but for this data in particular, we did a bit of a weird thing. We actually calculated synergy and redundancy, and then took the difference. We do this by pairs, right? So we pick two, calculate synergy and redundancy, pick every pair, because spoiler alert, we're later going to look at the topology of synergistic and redundant networks separately, and that's why we didn't do OIN for we did pairs. So it's two regions. So we calculated the synergy and redundancy between the past state of two regions and the future states. So to what extent do they jointly predict their future evolution? So they predict their dynamics. Thank you. So just from looking at this plot, we have this feeling that, or we have this intuition that redundancy is actually closer to the sensory periphery of brains. So your sensory regions and your motor regions are very redundant, and your associative regions and the regions that do quote-unquote the thinking are very synergistic. We can then actually formalize this by looking at the different resting state networks, and we see exactly what you would expect. Right? So if we look at kind of functional resting state networks, we see that redundancy is highest, and here positive is synergistic and negative is redundant. So redundancy is highest in the somatomotor network, and the salience network, and the visual network, whereas synergy is highest in the frontoparietal and the default mode network. For those of you that don't know brains, for example, the default mode network is where the default mode network is thought to generate our sense of self, right? And these kind of self-referential processes, like these very high-level cognitive processes. And you get a similar picture if you look at cytoarchitectonics. So the primary motor and primary sensory cortices are highest in redundancy. The associative cortices, where information comes together, are highest in synergy, which is surprisingly nice. Like it makes a surprising amount of sense, which the brain doesn't tend to. But that's exactly what it is. You can also look at cognitive relevance, so matching between these different brain regions and commonly reported cognitive functions for each brain region, and we see things like synergy is highest in areas related with high-level cognitive function. So these are the most synergistic regions. If you look at the cognitive tasks or the cognitive processes associated with those, you see very high-level things like cognitive control, social cognition, cued attention, autobiographical memory, and so on. Whereas if you look at the redundant regions, you see very low-level things like auditory processing, motor processing, visual perception, and so on. Right? So there's very clear distinction between high-level regions are synergistic and low-level regions are redundant. You can also look at the topology of the synergy and redundancy networks. And what we see is that the synergistic network is a lot more integrated or it has like much higher global efficiency, and the redundant network is a lot more modular. So there's like distinct topological qualities of these two. And interestingly, the redundant network is also much more aligned with the brain structure. So if you take a correlation between the brain structure connectivity, like the actual wires that run, between brain regions, those are a lot more correlated with the redundancy than with the synergy. So the synergy is sort of this emergent information sharing that is kind of hovering on top, and the redundancy is much more closely supported by the wires that are running across the brain. We didn't look at it. Thank you. No, so we have in this paper we didn't look at it. Sorry, yeah. No, so you can't. In this case, we could look at the unique information. We have since looked a bit at the unique information in subsequent papers. It's usually somewhere in between the two. The patterns are a lot less clear. That's also partly why we focus on these two, not being less known. So yeah, so the way we interpret this is as segregation, which is a concept that also has a long history in cognitive neuroscience. Right? So when you have functional segregation, this region is doing this computation and that region is doing that computation. Both of them have unique information about themselves, but not right? So there's that interpretation. We have some results in this, but they're far less straightforward to interpret things. So, but I can send you another paper if you want to see. Another quick thing to mention that we were also very surprised by is that synergistic neural circuits were uniquely favored by evolution. So if you put on the x-axis this synergy redundancy gradient, and on the y-axis the degree to which each cortical region expanded in the evolution between chimps and humans, you see this very nice correlation between the two, and same thing with human accelerated parts of the genome. Right? So it seems that the evolution sort of selectively picked regions of the brain that are doing these associative computations or synergistic computations in some capacity. We also see that I'm now breezing through things relatively quickly, but now we can draw this connection not only between synergy and cognition, but also between synergy and consciousness. So by looking at the brains of people that are in a coma or in unresponsive wakefulness syndrome, we see that the synergy of controlled subjects is much higher than the synergy of subjects in a minimally conscious state or in an unresponsive wakefulness syndrome. So what used to be called vegetative state now goes for unresponsive wakefulness. I am incredibly interested about the intersection between complexity science and consciousness. I'm going to leave it at this, but if you're interested too, come and find me in the coffee break. We have some other results on whole brain modeling, where we are able to make these models of coupled Stewart-Landau oscillators and add positive or negative connections and blah, blah, blah. We get some good stuff. I'm going to skip all of this in the interest of allowing myself a few minutes for the final part of the talk. So let's take a quick summary of what we've seen so far about the synergy in the brain. We've seen that redundancy supports perceptual and motor input and output to the brain, as we see from it being higher in sensory motor areas. Our kind of speculation is that redundancy is robust, right? So if you want a system that is processing some information, you really want the input and output to be as robust as possible, right? And that's where it makes sense that we find redundancy there. Whereas synergy supports high-level cognitive function, and it's higher in associative areas and in conscious states. Good. Now, for the final 3 or 4 minutes of my talk, let me talk very briefly about synergy in machines. And the overall goal in this part of our work is to ask, what is synergy good Right, so what is the functional role of synergy and redundancy? We have all of this correlational evidence from the brain, but we don't actually know if synergy or redundancy is playing a causal role in any of these computations or any of these cognitive processes. So we're going to focus on two learning systems. First, I'm going to talk about large language models, LLMs, that you may have heard of. And also we're going to say, maybe, some words about recurrent neural networks, or RNNs. I think I'll probably skip the RNNs, but feel free to ask if you want. So let me describe the experiments we did on LLMs. So what we did is we grabbed a bunch of open source, standard LLMs like Llama and Gemma and all these, and we pass a set of custom prompts. Then we record the L2 norm of the attention output as quote-unquote brain activity of the LLM, and we basically pretend those are fMRI time series, and we calculate synergy and redundancy using exactly the same procedure as before. So the way that the data looks is a bit funky, but it's sort of like this. So these are activities from two layers of one LLM, and we effectively have a notion of time. For those of you a bit more into machine learning, this is ultra-regressive times. So this is tokens. Effectively, you generate some tokens, and for each token, you record a value of the attention output for each head, and you grab these multivariate time series. And all of the results I'm going to show are replicated across 4. I think now it's actually 6. I'm letting the student continue working on this, so I'm going to show 4 LLMs, specifically 2 versions of Gemma and 2 versions of Llama with different numbers of parameters. And what we find, drumroll, is that LLMs have a synergistic core, very much like brains do. So much like brains, LLMs also have redundancy near the input and the output, and synergy in the middle. Right? So this is the same brain plot as we were looking at before. This here is the results from 4 LLMs, normalized such that 0 is the most redundant head, 1 is the most synergistic head, 0 here is the first layer, and 1 here is the last layer. And we see this beautiful inverted U shape, where again, the first layers, so near the input, are very redundant. The final layers near the output are also quite redundant, and it's only here in the middle that we see this peak in synergy, which is qualitatively the same as what we saw in brains. Interestingly, this doesn't happen when you initialize the LLM, right? So this core develops throughout training. I'm not showing the results here, but when you initialize, basically you get a flat line with noise, and as the LLM is trained, then this core actually shapes, and the shape of the U, the inverted U shape becomes more accentuated. And not only that, but the synergistic core in LLMs has similar network topology. So there's a really terrible plot that we need to improve. But TLDR, very much like in brains, the synergistic core in LLM has a higher global efficiency, so it's more interconnected, it's easier to send information around in longer paths. Whereas the redundant core, so redundant network, is a lot more modular, emphasizing you have like these clusters where information is shared, tightly within, but less, a bit more weakened across. So you have that same topological signature. And then finally, we can ask, are these synergistic heads functionally important? Or what we can do is an ablation study. Right? There's something that you cannot do so easily in brains, but in an LLM, you can grab all of your synergy redundancy values, you can identify the most synergistic heads, you can zap it, and you can see what it does. So what we do is we have this LLM, we run it in its kind of unadulterated form with 0 temperature, by the way. We grab a joint probability distribution of a bunch of feature tokens, then we zap up or ablate a bunch of heads, we rerun the LLM, and we get another probability distribution over feature tokens. And what we see to measure the divergence is what we calculate the KL divergence between those two trajectories. Meaning that because we don't really have a notion of right or wrong in here, but if this KL divergence is very high, that means that whatever perturbation we made has a very strong effect on the behavior of the LLM. And again, what we see is exactly what we wanted, where synergistic heads have a much stronger effect on model output. So let me walk you through this plot very quickly. Here we see the proportion of ablated heads on the x-axis. So here you're running the LLM as in its perfect condition. In here you're throwing out half of the attention heads in the LLM. The dashed lines are ablations at random, so you pick a certain percentage of the heads at random, you throw them out, and of course you we'll get some degradation in performance or some divergence in activity. But if you look at the solid lines, those correspond to the results of ablating the most synergistic heads. So for example, in here, you pick the 25% most synergistic heads, you ablate them, you see how much they affect the data. And effectively the gap between the dashed line and the solid line correspond to the specific causal role played by those synergistic heads. Right, so that's telling us that those synergistic heads are crucially important for that computation. And in fact, I will skip the recurrent networks and let me go straight to wrap up with some type of questions. So what I've been trying to show you throughout the last 40 or so minutes is that there are distinct roles of high order interactions in composite computation. So we have one side redundancy that provides reliable input and output to the system. It's higher in sensitive motor areas, it's robust to noise. And we also have synergy that supports general purpose high level cognition. It captures this notion of the whole being more than the sum of parts. And we see this from multiple sides, in brains, it is high in associative areas, in conscious states, and in artificial neural networks, synergy is higher in multitask networks, what we didn't cover, and on the most crucial heads of the LLM. So we have this convergent evidence from both brains and machines about the roles of these two different kinds of information. I'm going to leave it there so we have a bit of time for questions. Should you have any questions, please do come and find me in the coffee break or drop me a line. Thank you so much for listening.
Well, thank you very much, Pedro. That was excellent. And you were very successful in leaving a bit of time for questions, even though you had so much to say. So, okay, questions?
That's a good question. There's quite a bit of work on inferring high-order mechanisms from data, and usually, at the end of the day, it comes down to some inference process. Right? So you have to put some priors and write an alignment function and such and such. I have not worked on that myself, so I'm not an expert, but I do suspect there's a lot to say from synergy and redundancy. I'm happy to send a few papers if you're interested. It's not something I work on directly, so.
Thank you. Okay. You can use the mic, we can.
I have a question on the stuff you presented with the brains. I wonder up to what extent the redundancy that you obtain in, for example, somatosensory areas is due to the fact that the fMRI has a very low time scale, because I would expect these areas to process information in a very much faster time scale. So maybe if one looks at MEG or something like that, which part of these areas is redundant and which part is synergistic will completely change.
Yes, completely. I agree. I would really love to repeat this kind of study, but with much more multi-scale data. So, for example, looking at neuropixel data, looking at local fields, looking at MEG, and trying to compare a bunch of those. We have an upcoming piece of work where we compare MEG with fMRI, and we see that, for example, in MEG, there's a lot more unique information, and in fMRI, there's a lot more synergistic information. So I suspect that this joint temporal evolution, that like all of this strong synergy we find in fMRI, is because in one TR, so like in one time step of fMRI, you actually have lots of information exchange between brain regions. Right? And in that sense, what we see might be driven by this very big difference in time scale between our measurement and the underlying neural process. That's very much an open question. Thank you.
Yeah. Related with fMRI data,
Yeah.
synergy and redundancy depends on the coarse grain, the size of the coarse grain, and if this is true, what is the effect that the mask have different size for each region?
Good question. You're referring in particular to the parcellation. Yeah, so all of these results were replicated with a range of parcellations, both functional and anatomical. So we look at shapes for parcellations of different scales, like from 1 to 500, as well as AAL and a bunch of others. So, correct. Yes, correct. And the results are the same. That's the point I want to make, right? So the results are pretty consistent across parcellations of different sizes. I am very mindful that there will be differences because you're averaging more or less sources of noise and blah blah blah. I don't know exactly how that works, but I am fairly confident that the results you've seen here do not depend crucially on the partitions being of a given size, because it's quite obvious.
Hello, Pedro. Hi, talk, and really nice talk. I have a question. It's kind of related, I think, to what the other colleague asked. When you show us that redundancy regions usually capture more the structural details of the like how the things are really wired. I have a paper with Joaquin about topological reconstruction through data. What basically we did is we have in vitro data of neuronal tissue, and we decompose the transfer entropy, right? And use the different atoms to reconstruct the network.
Yeah.
In that case, we saw that the unique information give us far more details about the structure than the redundancy. But I'm thinking now, why is that, right? Maybe, do you think could be related to the time scale of the data, to, right? Again,
I think
in
so.
that case?
I
It's like
think
yeah, it's like you make, but I go even a lower scale there, right? By looking calcium signal in the tissue, and then you see the structural details are coded somehow. Like the information is in the unique transfer, right?
Yeah,
So-
no, really good point. I really like that paper, by the way. I suspect that there's a big effect of time scale here, as our colleague was mentioning earlier,
Yeah.
right? That maybe we see redundancy because we're looking at a core time scale, and therefore we have all of like so much
Yeah.
information exchange, and the tight, like the direct connections encourage this direct sharing or copying of information.
Yeah. And the other thing, again related to time, is I don't remember clearly, but I think Thomas Varley have some papers when he basically measures something similar to you, but in time, right? He kind of measured this kind of to this kind of analysis in time with this data, and if I to remember wrongly, they showed that the same region can change in time from synergy to redundancy and keep changing, right? Even if you look.
Yeah.
So maybe it's not that simple, right? To say this region is always synergistic or always brain is a dynamic entity. They're changing
Yes.
the way it's processing information all the time.
Yeah, exactly.
And this more
That's,
as always, right? It's always much more complex picture.
yes. Yeah, tends to be the case. So big caveat to all of this is resting state average from a long scan.
Okay.
Right. So how would this change if you look at time result dynamics or if you look at task? Right? Like for example, what happens if I show you a picture of something and I ask you to press some buttons? There's a huge amount of processing that happens in this span of say 300-400 milliseconds. So it'd be great to get a very fine time result picture of all of this, which we don't have yet. We're working on it. But yeah, this is all taking a very crude average.
Okay. Yes. Okay.
I have a question. You put transparency about the definition, well, to visualize redundancy and synergy. And it seems to me that could be very related with the synchronization phenomena. So I understand equivalent to redundancy, phase locking, all oscillator working together. But what about synergetic? There is a direct translation between the synchronization phenomena. I think it's quite interesting because since many years, people have studied synchronization phenomena in the brain in many places, in the Kuramoto oscillators. So how all these information measures relate with synchronization?
Yes, really good question. Really good question. I have two answers, a short one and a long one. Let me start with the short one. Empirically, we see that synergy peaks in metastable regimes. So we have a couple of studies of Kuramoto oscillators where you get them close to a critical point, there's stability, then you also have a nice big peak in synergy. So empirically, there seems to be a correlation with metastability. Now, in terms of synchronization being redundant or synergistic, this is something that Fernando and I thought about for a long time, some years ago. It turns out that most of the measures we typically use for synchronization, such as the Kuramoto autoparameter, they're actually redundant. Right? Like with Kuramoto autoparameter, you cannot have 3 oscillators that are more synchronized than 2 oscillators, for example. So it's intrinsically quote-unquote redundant. We came up with some measures of synergistic synchronization and some of Synapro systems that were synergistically synchronized. We went and showed this in a conference in processor systems in Barcelona. And all of the oscillations people that came around and looked at it, basically looked at the time series of our system, were like, I don't know what this is, but it does not look synchronized to me. And that's where it ended, basically. So I think there's a notion, yes, you can describe something that theoretically you can describe as synergistic synchronization, but it does not look like things going together at the same time. So our intuition of synchronization is a bit stretched. And I would say that if you want to keep that intuition, then synchronization is intrinsically relevant. So maybe the dichotomy is between synchrony and synchrony. Yeah, but like very interesting topic. I'll be keen to talk about.
Okay, well, thank you very much again. Let's thank the speaker.
Control fairly reverse.
Okay, so our next speaker is Daniel Freiman. He's going to talk about universality classes in traffic jams. So, please.
Okay. Okay. Thank you, Joaquin, and all organizers for giving me the opportunity to be in this nice meeting and this beautiful city. I'm going to talk about universal class in a traffic jam model. The model here, though it's not so important. The idea is to show, to see some a particular question that we made inspired new ideas. So, what is the model? The model is just a one-line road. Suppose you want to go from here, Granada, to Madrid, and cars appear at different positions, and they want to go at certain speed. Okay, and a more realistic view of this model can be here in a mountain road where you cannot pass, and this is Capilera. If you have any opportunity of going there, it's a very nice village, and you will have this type of road. So the model is extremely simple. At time 0, we have these cars that are these yellow points at certain positions, and they want to, with an initial velocity, and they want to travel at this constant speed, but there is a car ahead of us, perhaps, that wants to travel at a smaller speed, and then jumps are generated. So what is in this example, the car number 5 wants to travel at 75.2 kilometers, and then you have a jam of 5 cars. The other one wants to travel at 81.6, and you have a jam of 6 cars, and the last one is 2. Okay? So finally, we have 3 jams in this example where we have just 13 cars, and the size of each jam is 5, 6, and 2. So a little of notation says y will be the initial positions, and v1, v2, vn will be the initial velocities. And now we will have n cars or vehicles, and we are going to study what, for example, xn
is the number of effective cars at time t, and this converge to x tilde n, that is the final number of jumps. So, and we are going to study this x tilde n and the size of each jump, this vector m that has the size of each jump. In this example, n is 13, we have x tilde 3, because we have 3 final jumps, and the mass vector is 6, 5, 6, 2. So, which are the hypotheses of the model? The hypotheses are that the B1, B2, Bn is an IID sequence of random variables with distribution f. The f must be continuous, not to have ties, and the sequence must be independent. And there is, in principle, there is no distribution hypothesis for the positions, and the questions we want to. The first question is what can be said about xn till x tilde n and vector m. So, first note that if we just put in this graph the initial conditions, in the x-axis the initial position and the y-axis the velocity, and we look from right to left, I'm going to mark some particular points or cars. That is the first one, then the one that is at the left that has a lower velocity, and the last one. And these are exactly the jumps. What's the point about this? The first thing is we don't need time evolution if we want to know how many jumps we will have. And this will be related with record theory. I think many people here in the audience are known about record theory. For example, we can think about temperature and trying to understand the effect of temperature in the effect of, for example, okay, don't worry. Each year we have a maximum temperature, and we want to know if this temperature is maximum, is a record or not. And basically the question is, has the climate change any effect on that? If data is IID, there is no effect. And if you are having records very near in time, then the hypothesis of IID is not correct, so there is a real effect. So just remember what is a record. A record is if you have a sequence of random variables, xk is a record if xk is the largest between the previous ones, or if it's the minimum. You can add the maximum temperature or minimum temperature, and the first variable is always is considered a record. So, related now with jumps, we were interested in understanding how many jumps we will have. And from record theory, we know that the probability law of having k records or k jumps, it's like a Poisson distribution. It's not exactly a Poisson distribution, but it's very similar. For example, the expected value goes as log n. If you have n cars, you will have in average log n jumps. And the variance, as you see, goes also as log n. That's why it's like a Poisson distribution. Okay. And now if you study the number of final jumps of S cars, the expected value of the number of cars of S cars, the number of jumps, car is 1 over S. And this is the first indication of criticality with a power law decay 1. And something curious is that the expectation does not depend on the size of the number of cars. It's always 1 over S. And now if we want to study something about time, we can study, for example, the last collision time. It's the last time where the final jumps are generated. And what we see is this depends on the law F, of the probability law of the velocities, and on the size of the number of cars, let's say. But we can collapse these by a proper scaling and see that it goes like 1 over t. So now I'm going to put the question that I think can be interesting here. The question is, what are modes belong to the same universality class? This question is, I'm not going to compare this model with this model and see if they are in the same universality class. What I want to know is, give me more models that are in the same class. Okay? As far as I know, this question has not been answered. So, particularly what we mean about being in the same universality class, we're going to say that we want to find other models that satisfy these two equations. That the probability law of having k jumps that can be other things, not jumps, has this formula, and that the expected number of jumps of size S goes as 1 over S. Okay? So that's the question. And in order to give an answer to this question, the first thing is to try to describe the number of final jumps x till the n and the mass in a formula. A formula will be possible because we know we don't need time evolution in this system, and this is the formula. Okay, W is basically the velocity that we put another particle, another car, an artificial that have 2 times the maximum velocity, but this is just an auxiliary point to make easier the formulas. And you can compute, given a vector of velocities, what is the number of jumps and what is the mass of each jump, okay, by this formula. Okay, this formula has a particular, here, the mass of a jump, in order to find the mass of a jump, you have to find a coordinate, a car in this order sequence, that has a velocity that is smaller than all the ones that are below it. This is like the picture. You have to find the smaller velocity, which is smaller than any other that is further to it. Okay? So, for example, the minimum velocity between from 1 to 5 is smaller than from 6 to 8. So, there are 2 ways to put this mass based on the velocity vector. One is like it's here, just Wj smaller than Wy, or put in a formula that is the minimum of this vector. Okay, it's equivalent. So now the point is, here we have a minimum, okay? And what we are going to say is, okay, why put in a minimum? Why not just think to have another function that behaves in a similar way? Let me put it this way. So we will change this minimum by a g function, and now we ask which function g satisfies these two equations. And the function g that satisfies these two equations will be the ones that will generate new models. Okay? Okay. If we use G as the minimum or just WG, we have traffic jams. And this is the main result. The main result says that a function G that verifies some conditions and also satisfies this. When considering x n tilde and m by equation 1 and 2 that are these two equations. Okay? Xn and m is given by this equation, and now we have some conditions about g functions that will generate this class of products. So this that seems a strange condition, the proof is built on two early papers outside the literature on records and traffic jams. One is from 1964 and the other one 1999 in combinatorial lemma and other things. So let me show you examples of this G function. So G0 we know that verified, but we have, for example, model 1. What is model 1? Model 1 is take G as just the average of the velocities. Or take G, model K, with K greater or equal than 1, just what can be considered the empirical moment K of the data. Okay, just the average, but with power K. Or model F can be take the average of any function over the coordinates. So here we have infinite models that verifies equation 1 and 2, that verifies that the probability law is the one that we want and the expected value the same. So now we have to interpret some of these equations. Some of these G what models give. And let's start with model 1. Okay? Model 1 is to use this average. And to use this average is just to have a one-dimensional model of fusion particles with perfectly plastic collisions, where there is momentum conservation. You know, when two particles collide and merge, we have a velocity that is the average. So, and if you have a fusion of k particles, the velocity of these will be the average velocity. So if we start with a configuration of one-dimensional space with 3 particles, we can have these 3 configurations that will give a final number of particles that can be 1, 2, or 3. Okay? So now the model is like this, and now the concept, the x tilde n will be the number of final particles, and the mass now it's the m is it's okay, the letter m, because now we have the mass of each particle. And in this example, we have 3 particles, 3 final fused particles, and the mass vector is 3, 6, 1. And this verifies that the probability law is the one that we want to have, and that the expected number of final particle of mass S is 1 over S. Also, if we study the last collision distribution, in this case, we have this power law of 1 over T. So, we start with model 0, that is a model of traffic jams that related with G gives this behavior. Then we studied the model 1, that is the average, that is perfectly plastic collision, a physical model. And finally, we can try to understand what is this type of behavior. With a model where the G function is the second momentum, okay? The average, the empirical second. So again, we have to interpret this model, and the way we can interpret this model is the following. Let's suppose you have a recipient where you have n particles, okay? And now you do a small hole in this recipient, and the particles enter to a big container, okay? But you have a magic ball, a crystal ball that you know what is the velocity of each of the particles that will get out from the small recipient. And now you make a question that is, okay, if you know the velocity of each one, and if I give you walls that you can put in the container, are you able to do a gradient of temperatures? And the answer is yes. And this is exactly the G function with square. Basically, you are looking for putting to trap particles in order that the average velocity in each container, small container, is smaller than the other one. We have the same effect that we want smaller things on the left and higher on the right, but can be velocities or can be, for example, square velocities. So in this case, we have that we can do we can have a gradient of temperatures, and the number of clusters will be xn, x tilde n, that is like the analogous of the number of jams, and how many particles we have in each cluster is the mass vector. So in these three models, we have that these two equations are verified. That's why we say that they belong to the same universality class. So, in summary, we show that one-dimensional traffic jam model typify a universality class that governs cluster formation in systems driven by a single scalar variable. Within this class, infinitely many models were characterized. Then you have to interpret them. And the concept and result presented here may help elucidate other non-equilibrium systems. Thank you.
Well, thank you very much, Daniel. Really interesting, and we have a bit of time for questions. But, yeah.
Thank you, Daniel. Very nice, interesting talk. So I have many questions. So can you generalize, because you start with a very simple one-dimensional traffic jam. I'm not expert in this research field, but I suppose there are many other type of traffic jam models, more complex. Maybe they follow a different law, like the one you presented here. I don't know. Do you think? Do you have in mind it's possible to extend this analytical process to classify models from different concepts or matters to these these other systems with a different? It's possible. Do you think it's possible to do the same mathematics?
Okay, that's the idea of this talk. I'm not expert in traffic jams. I like the model because it's really very simple, as you have observed. But I think the most important part of this is to try to say, okay, what really characterizes the model? And here we have two equations. And in other models that can be traffic jams or any other non-equilibrium system, if you're able to say, okay, these are the two free equations, and now how to put this g function is the difficult part, let's say, and say, okay, which g function are compatible with these three equations. But the methodology must be like the natural way will be that.
So I was just thinking, I assumed you were going to talk about the critical point between like a sort of gas phase where all the cars are independent and like a liquid phase where they all have to move together. So it would make sense that you get this sort of distribution, like a scale-free distribution at the critical point. But I don't see where the criticality comes in. To me, it looks like it applies to any density.
It's a non-equilibrium system.
So it applies at any density.
You always finish by, you always, there is no alternative to this situation.
Yeah, so that's it. So it doesn't depend on the density.
No, it doesn't depend on the density. No.
You always get the 1 over S.
Yeah. That's the way the model is extremely simple.
Okay, any other questions? If not, thank you again very much. Okay, so the next speaker is Paco, or Francisco Perez Reche, and he is going to talk to us about synergistic epidemics, multi-stability and dynamic higher order interactions on networks. So thank you, Paco.
Okay, thank you very much. Thank you very much for for the opportunity to present this research here. And well, yeah, the name is Paco normally, everyone that knows me calls me Paco. Francisco seems to be too serious or something, or at least longer. Anyway, so the talk will have, in some sense, it will have a classical flavor, yeah, in the sense that I will talk about epidemiological models that most of you know very well. I will have to go through it just to introduce things, yeah, but bear with me. Things might get more interesting towards the end, if I make it to the end, because process. Yeah, so if I control time properly. And then there will be some new ingredients, which is synergy. Yeah, we call it synergy. And in the first talk by Pedro, there were mentions about synergy and so on. Maybe we use the word in a slightly different way in this context. So we call it synergistic dynamics. And yeah, and there will be bifurcations, which you might think, well, it's something very classical. Yeah, what's the point of it? Well, I hope you find something interesting in that. So let me start in a very basic way. So you may want to model spread of infection, spread of social contact, behavior, misbehavior. Yeah. And a paradigm is, models with this kind of 3 states. You can have more states. And of course, during the COVID pandemic, everyone learned about, if someone didn't know about these models before, everyone learned about them and work on them. Yeah? So, well, depending on the context, you may say, well, you have a susceptible individual, and well, if it's a pathogen context, yeah, so susceptible, infected, removed, or die, recovered, whatever. And then in social content, you may call them ignorant, spread, stifler, whatever. Yeah, so the stifler is someone that forgot about the rumor. So this is the setting, and then there are 2 classical ways to describe the transmission of infection, and I will use infection as a paradigm. Of course, it could be social contact. Yeah. So there is a SIS model where you have only susceptible and infected, and what happens is that susceptible individuals, they come in contact with an infected, and then after a while, susceptible recover, but they don't die. They just recover from the disease, and they can get infected. This happens with these rates, lambda. Yeah. Then the SIR model is the same, in terms of infection, but then what happens after is different. So individuals become completely immune to the disease, or essentially removed, don't get the disease anymore. Right, so I will deal mostly with this one. Yeah? And anyway, so let me start constructing here a kind of conceptual space for models. Yeah. So in terms of infection dynamics, I will be dealing with SIR and SIS, mostly with SIS. Now, next thing is, how does transmission occur? Yeah. So the simple transmission is, you assume that if there are 2 pairs of individuals, for instance, one of you is infected and I'm susceptible, yeah, then, well, the transmission of the infection maybe happens it only depends on you and me. So this is what most models assume. But in reality, if there are more people around, I might decide to use a face mask. If some of my acquaintances are using a face mask, I might imitate them and say, oh, maybe they are susceptible, they are using a face mask, they will use a face mask. So in this way, what happens is that the surroundings are affecting my way of describing, or whether I become infected or not. So the surroundings are affecting this lambda transmission. And this is what we call synergistic transmission. Yeah, so this is very, very generic. I'm not specifying yet what kind of synergy here, but this is the basic idea. Yeah. So I will be dealing with this kind of models, and so just constructing the model space. Here we have the transmission dimension, say, and well, normally epidemiological models deal with pairs, but we will be looking at the role of higher order things, the surroundings, and that we call synergy. Now, next thing is, of course, we have to connect individuals somehow. And so what we need is to know who transmits to whom, yeah? And this is the network of contacts. Here I am plotting a couple of examples. first one is one in which all individuals are connected to 3 neighbors. This is a k-regular graph of degree 3, and this is a more complicated one in which some individuals are connected to more neighbors than others. Yeah? So this is a heterogeneous network. I'm just putting these 2 examples because it will be within the context of synergistic epidemics. Now, what about SIR model? What happens with this model? Well, we started, sorry for the crowded slide. It's not so important in the sense that I will not be talking about the SIR model, but we started working on the SIR model with synergy. Right? So we did some work on that. It's interesting and so on, but I will not deal with it in this talk. Right? So if someone is interested, I can share the slides and you can get the keyword focus. So interesting, but I will focus on SIS. So basically, what I will be doing is SIS inflection, and then I will be dealing with synergy, also pairs, of course, and different types of networks. Now, in terms of notation, well, I have introduced already lambda and mu, the transmission rate, the recovery rate. Now, one can deal with 2 different dynamics. You can say, okay, so continuous time dynamics is when I consider time steps that tend to 0. And, but actually we will be dealing with discrete dynamics, saying, okay, so there is the clock only ticks every 1 unit of time. Yeah? Okay, so my delta t is 1. So it means that this lambda and mu become, before they were rates, but now they will be propagated. They are between 0 and 1. Why will I focus on this one? Because basically the phenomenology of this one encompasses. Now, this is important. So, how do we introduce synergy? This is a new ingredient in our model. Well, we call it as synergy. The one I will consider here. We studied other types, but the one I will be considering here is what we call the synergy. And this is basically, imagine you have here a donor, well, an infected individual, and here a susceptible. Right, so S synergy comes from the fact that we assume that this transmission actually depends on how many susceptible neighbors this guy has. So basically, what does it mean? So perhaps you are trying to sell a product to someone, yeah, and this one has heard from their neighbors that the product is not so good. So then this lambda, the chance that this one will buy the product is affected by it. So this is our lambda n. N here is the number of infected. So kind of mathematically more convenient to deal with the number of infected. The number of infected, of course, is the node degree, this one, minus the number of susceptible. So we have an intrinsic rate transmission, or intrinsic probability transmission, which is without synergy, say, and this function here, which accounts for the effect of the neighbors. Now, so just in particular, we use this functional dependence on the number of susceptibles, which is k minus n. Yeah? N is the number of infected. We use this exponential because we want this function to be non-negative, and this minimum here, it kind of imposes the fact that this function will be between 0 and 1, which is a probability, this is a discrete time. Right, so, and this is a synergistic strength. Yeah, so this is a new ingredient. Beta is a synergistic strength. So for instance, when beta is negative, it means that lambda will decrease with the number of susceptibles, k minus. Yeah. And this means, for instance, I protect myself using a face mask. If others do reinforcement? Well, it might mean that actually you realize that no one has bought the product. You think the product is good, and everyone will want to buy it. For instance, I know the case of someone that before the COVID pandemic bought many face masks. This guy was Chinese in China. He made a lot of money. Okay, so he decided to buy many face masks, and of course, when an epidemic came, he had many face masks. So this is the reinforcement. Yeah? The most interesting one will be this one, yeah? For us. Now, what we want to do is answer the question: is the network vulnerable to infection? So will the infection spread? And for this, we focus on the long time limit. And well, there are two ways to analyzing the model that we address. Yeah, one is numerically, so you use Monte Carlo simulations, network, and simulate this. And the other is, using some approximations which give mathematical insight. Yeah? So it's a single site heterogeneous midfield, SSHMF. Yeah. So let me call it. And both approaches agree. Okay. So what I will present here, just to bother you with some bifurcations and so on, is a mathematical kind of solution. Yeah. Okay, so it's this single site heterogeneous midfield. So single site means that basically if you have this setting here, the probability that this happens, yeah, which is that this individual is susceptible, this one is infected, susceptible, you kind of separate it into independent probability for each of them. This is what it's been done many times. It's not something new. So I'm just presenting it systematically, but it's not new. The other approximation is heterogeneous midfield. It means that, of course, the probability that an individual, this one, is infected, will depend on its node degree, but it will also depend on what happens to the rest. But we'll assume that actually the probability of a node to be infected only depends on its node degree, so how many neighbors. And then, therefore, the node degree distribution is sufficient. The rho k, that I will call it, is sufficient to describe it. You don't need to know actually other topological features of the network if the node degree distribution is correct. Now, sorry for all the equations here, but basically, I'm sure many of you have seen this kind of equation before. You can derive this from a master equation, but basically, in this case, for discrete time, you say, well, the probability of an individual with node degree k of being infected at time t plus 1, these are the parameters of the model, yes, the alpha, beta, t, and so on, is equal to, this, the probability that it was infected before, and then this one is just the term that comes from this probability here that the susceptible node becomes infected. Okay, so you have these contributions, and you can write everything in terms of this zeta here, which is the probability that any neighbor of a recipient node is infected. Okay, so you go to a node that is being challenged by other nodes and look around, and then this zeta is just telling you what is the probability that the neighbors of this one are infected. So I'm relatively quick with this explanation because I want to proceed further. So basically, by looking at the long time limit, what happens is that we take the time going to infinity, so we want to find fixed points of this equation. We make this one equal to pk, yeah? And therefore we find the probability pk at time infinity, yeah, which is given by this. Basically, what everything reduces to is to finding the zeros of this function. Yeah? Okay. So this function, I have to find the zeros. And here is where the bifurcations and so on will come. Yeah? So this function, I find the zeros, it will give me roots. Yeah? So these roots will tell me how, the states that exist time going to infinity. Okay? And then finally, what I will look at is at the expected proportion of infected nodes. So I want to know how many nodes, on average, I have infected time infinity. This is what I'm interested in. And then, of course, I will vary the parameters, the alpha, the betas, of the synergy parameter, and so on, and see how things change. Now, let's go back to something that most of you will know, which is when I have no synergy, so the normal SIS model. Normal SIS model, well, what happens is that the probability that, remember that this P is expected proportion of infected nodes at the end, is 0 below a certain value of the transmission rate, and then here there is transcritical bifurcation in which infection is a stable solution, and this one, the no infection one, is unstable. So, the arrows indicate this. Now, one can prove actually that in this case, no synergy for any network within the mean field approach. You have only these two regimes: the one, the disease-free one, and the one in which disease is endemic. This is one can do it for any network. Now, so here we have a transcritical bifurcation. It's the first mention of bifurcations here in the talk. So basically, you go from this regime in which only this state is stable, so 0, 0 zeta, 0 p, and then you go to a regime in which this one is unstable and this one is stable. The endemic one is stable. So basically, here you have a bifurcation that I call TC minus because the unstable part is on the left and the stable part is on the right. So there will be TC plus. Good. So this is without synergy. Now let's see what happens when I include synergy in homogeneous networks. So I take a k-regular graph and I include synergy. Well, here I have my beta because I have synergy. So what happens is that for high values of beta, I find a transcritical bifurcation again. The same as for the non-synergistic one. But when beta is more, is negative, meaning more opposition, I imitate more those mass and so on. Then we find this kind of saddle node bifurcation. So when increasing alpha, like this, the system goes through a saddle node bifurcation, which is this one here, and then it finalizes in a TC plus, which goes to the endemic state. So this basically tells you that if you come like this, then you will jump here, and this is the so-called explosive mutation. And things go viral suddenly, even if there is opposition. So in the idea, go viral sometimes. Most of them will not go viral, but if any of them goes viral, it will be explosive because no one would like to adopt them initially until there is enough kind of mass, and then everyone adopts them. We've seen examples. Now, this is a situation in which you have here this subtle node transcritical bifurcation appears here, which kind of comes from the collision of this subtle node and transcritical bifurcation. This one, SN and TC, these are codimension 1 bifurcations, and this one is codimension 2. So this is our setting here. When we have homogeneous networks and synergy. So this SN appears, and then you have an extra regime. You have this regime here, in which the two, the disease-free and the endemic coexist. Yeah. There is coexistence. This is new regime. Disease-free and endemic are stable. Now, what happened? Well, okay, before that. So these three states have been found in many systems with higher order interactions. Before us, after us, and so on. Yeah. So here is an example of infection spread using, you know, the higher order interactions somehow are kind of represented by simulation models. Now the question is, there are three states for all these higher order ones that have been published. The question is there anything else? Is this three states all? We have all this, you know, the coexistence between the endemic and the disease-free, or is there anything else? Because without synergy, we had two states, and this was robust against, like changing the network and so on. So this is the case in this case when you have synergy. Well, the truth is, we recently published this paper in which we dealt with heterogeneous networks instead of only homogeneous, and we found that actually things are much more complicated. So the thing is that this function that we want to find the zeros of, is non-linear, of course, and when you introduce heterogeneity, this side of the equation can become quite non-linear. Therefore, you get many roots. We studied several types of networks, real networks, model networks, concerning dash. So we applied these ideas to types of networks. All of them kind of give the same kind of phenomenon. This is a case in which, you know, this extends somehow what I presented for homogeneous networks. So this regime and this regime are the same as homogeneous networks. But then as we make beta even more negative, we find situations in which, for instance, you know, we have an endemic one here, instead of just this one and this one. And here we have the endemic is separated by this one by a kind of unstable branch, and so on. So many more bifurcations appear. I will not describe all of them in detail, obviously. Don't worry. But many more bifurcations appear, and therefore many more possibilities for the probability of infection versus my alpha transmission rate are possible. And this is the whole graph, which highlighted. It took a while for us to kind of come up with it. I know it's a bit messy, but this is how you relate, you know, all the regimes with all these dimension one bifurcations. Now, finally, I want to say that, of course, these are codimension one bifurcations, but there are, we found up to codimension four bifurcations. This, I will not go in detail in the interest of time. So here, this is the definition of a bifurcation set. So it's a set of parameters. You know, you have a region in your space of parameters in which these things happen. So depending on how many derivatives of this function f become zero, well, how many derivatives, meaning the L derivative, you can find bifurcations of increasing codimension. So the codimension is how many parameters you have to tune to kind of find the bifurcation. In here, all these ones here, the SNT, this SNT, they have to tune to parameters, dimensions. But you have many more, okay? So you have, we had to come up with weird names for all these bifurcations. So this is the dimension 2 saddle node transcritical cascade. Cascade is quite well known, which comes from the collision of a saddle node, but you can go up and inventing longer and longer names. I guess there is a better way to do that. And just to say that, of course, one can vary other parameters and find, locate all these bifurcations in the parameter space. And the other thing is that you may say, well, if I have a network, then I predict what will happen when I add synergy. And I think it's very difficult if you have to really do the calculation. Because this is, for instance, for a power law. The other one I presented before was for so this one here is for a binary graph, and it's quite different. Yeah, so what do you find? So it depends a lot on the network. This I will say, and go to the conclusion. So I've been talking about synergy, which is pairwise interaction. Which, basically, transmission depends on the neighbors of the pair I'm considering, and well, we found rich dynamics. I hope I have convinced you that with all these bifurcations, it's quite complex, and you may be wondering, well, what is the interest in that? But I think it's nice to kind of classify all these bifurcations because I think with the kind of popularity of higher order interactions nowadays, dynamical systems will find more and more kind of complex bifurcations, and I think making the effort to classify is interesting. And I think the phenomenology applies to conjecture. I'm sure it applies to the SAR, and yeah, so this is also computation and so on.
Thank you very much. That was really interesting. Oh, okay, question already.
Thank you, Paco. I have a question about numerical simulations. Have you done stochastic simulations in those cases in which you have coexistence of the endemic and epidemic regime? Because that has to be really fascinating to observe, like in a network.
Yes, we've done that, and we find, for instance, when we go to the real networks, just to make it more kind of interesting. If you look at the one network, the blue one, it has a very clear degree distribution. We find cusps, we find up to, I mentioned 3, I think, for this one. And yes, with the numerical simulations, you can kind of recover the same phenomena, and you can find this kind of situations with two endemic states coexisting.
So thanks for this very interesting talk. There have been a couple of publications over the last years on multi-species dynamics. So when you have COVID-19 and the flu acting simultaneously on a population, or rumor spreading combined with infectious dynamics and so on. Are these equivalent to your approach, where you say you put in this nonlinearity, or is there a substantial difference in these approaches?
I guess I would need to know better, the models you were talking about. Superficially, I would say maybe not completely equivalent, but maybe there are nonlinearities that appear that actually could be analyzed. Because I think in many models that people have analyzed in the past, there might have been this kind of complex, bifurcations and so on, and they have not been discovered because very often what you do is you do an expansion around the disease-free state, and with this you might miss some nonlinearities that might give you a more complex behavior. So my answer is I don't know, but probably there will be nonlinearities that might lead to this kind of complex.
Very nice talk, Paco. So it was not clear from your talk if all this characterization of the bifurcation you showed us due to high order interactions are numerical results or are analytical results. So I am telling that because that sometimes you can characterize this bifurcation by means in the normal forms of the bifurcation. No? And I don't know if you, in these complex networks you were able to find maybe within some approach this normal form. So there's some other speaker this that for example in some that in some model with triadic interactions, a kind of priority interaction, they can obtain a map within a mean field that show similar or some, for example, period double bifurcation in another complex. Do you think with your models you can extract this normal form?
Yes, I think it will be possible, and it's basically encoded in this set, which tells you which derivatives are seen. So basically, we have a long version of the paper, but basically we started before coming up with this kind of nice, which I think is a nice way of finding a information. We thought about logging. So we have all these expansions. And basically, when you take which values are seen, so
Any other questions? Okay, no, well, in that case, let's thank the speaker again. And yeah, now it's time for the coffee break. And we're doing quite well for time, I think. So I think we come back at 11:20. And I've just remembered, I think you said yesterday we'll be doing a photo. Yeah, should we do that at the end of the coffee break? Okay, so at the end of the coffee break, before we come back into the room, we all go down. Oh, it's true. I was thinking we could do it, yeah. Okay, but be photogenic for the end of the coffee break. Okay. I'm getting as photogenic as I can with my coffee already, preparing some patterns, so do what you can. Thank you.